our determination of the rate law for the crystal violet reaction here first. So we'll talk about the rate law from the observations, but we're going to do two runs here. Run one is going to be 15 milliliters of water, 5 milliliters of sodium hydroxide, and 10 milliliters of crystal violet. So the total volume here is going to be how many milliliters? 30 milliliters. And the crystal violet is going to be a 10 to 30 dilution, or 1/3 dilution. A 1/3 dilution should bring it into the Beer's law range, correct? What do you think? Probably? Yeah. All right. So we need to set this up. Now the procedure is written for a different setup. Since we have the LabQuest system, what we can do is we can just program this. So we don't actually have to take our observations. What LabQuest is going to do is it's going to sample the absorption at different intervals. So we'll set that up together, the experiment. Then for run two, it's going to be 10 milliliters of deionized water. We don't have any distilled water. 10 milliliters of sodium hydroxide solution and 10 milliliters. So again, it's going to be 10 to 30 dilution for the crystal violet. However, for the sodium hydroxide, up here it's a 5 to 30 dilution. Here it's a 10 to 30 dilution. So it's going to be twice as concentrated in run two. So if we increase the concentration of the sodium hydroxide, does the reaction speed up, slow down, or stay the same? So that's what we want to observe. It actually speeds up here, so we'll see that. And so we'll do the data collection for this. For the sodium hydroxide, though, what was the concentration of the sodium hydroxide standard that they give you? Yeah, 0.11. 0.1 is about twice as concentrated as we wanted. Otherwise, we don't want the reaction to go too fast. If the reaction goes too fast, then we aren't going to collect much data. So we want it to be about the right amount. The right amount is going to be actually, I was wrong last time. I said about 30 minutes, but it's less. It's more like 15 minutes. 15 minutes for the slow one and even shorter for the fast one. So what we're going to do is we're going to do a 1 to 2 dilution of our sodium hydroxide. So this is why they gave you a 100 milliliter volumetric flask. The 100 milliliter volumetric flask was to dilute the sodium hydroxide by a 1 to 2 dilution. So here they're talking about preparing a rinse solution of sodium hydroxide. Your final rinse is always going to be the solution that you're going to dispense, because we don't want DI water in there that's going to contaminate our standards, change the concentration. And so we're going to save about 20 milliliters of sodium hydroxide for the rinse. And then what are they doing? They're asking for two 25 milliliter pipette portions into the 100 milliliter flask and then dilute it with water. So that's going to make a 1 to 2 dilution. And so we'll just cut the concentration in half. It's going to be 0.05, but this is not enough precision. That's not enough precision because, standard solution, we know the concentration with a pretty good degree of precision as well as accuracy. And so up there, this is more like a 0.05 XXX. The standard solution is known to 4 sig figs. Therefore, our diluted solution should be to 4 sig figs because our volumetric flask is also very precise. Our volumetric flask is 5 sig figs. It's actually 100.00 milliliters. And so that's 5 sig figs from our volumetric flask, 100.00 milliliters. And our pipettes are good to 4 sig figs. It says 25 milliliter pipettes, but these have been calibrated to 25.00, not 25. So that's 4 sig figs. So we should be able to get 4 sig figs in our diluted solution here. So I'll talk about setting this up after. Talking about a couple of other things here. Let me see. So we're going to leave the kinetics lab for a moment, and then we're going to take a look at our crystals. Hopefully you have some crystals in there, and hopefully the solution hasn't dried out completely. Why do we need the solution there? We need the solution there to make sure that the impurities stay dissolved in the solution. So just a little bit of solution. Oops, not what I wanted. What types of impurities do we expect in the solution? You know, the types of impurities that we expect in the solution would be things like excess oxalic acid. Maybe we don't have much excess oxalic acid, but definitely excess like potassium oxalate we should have. The potassium oxalate, oxalic acid potentially, etc. These are white solids here. In solid form, hopefully these will be in aqueous form. In aqueous, we just have a CCS. In solid form, these are going to be a white solid. If you let all the water evaporate, then we're just going to be left with a solid, white solid residue, which is going to contaminate. So we're going to get co-precipitation. Co-precipitation means not only do we get the crystals that we want, we get the crystals that we don't want. And we don't want any of this white solid. I know that some people, their liquid has evaporated, but we have a problem here because if we add more liquid, we're going to lose some of the crystals. And also some of the crystals when they dissolve, you'll lose some of the characteristics of the crystals. Let's say I have a crystal like this. When you dissolve a crystal, what gets attacked first? This is like a sugar cube. If you dissolve a sugar cube in, let's say, coffee or water or whatever, you dissolve a sugar cube, which sugar molecules get attacked first? The corners. And so what's going to happen is the corners are going to round. Hopefully we don't want that to happen because we need to know the shape. After the corners start to round, then what else starts to round? So we're going to lose the corners, and then we're going to lose the edges next. And they'll start to lose their shape. And the shape of the crystal is important because the shape of the crystal helps us identify what it is. You know, different things crystallize in the different shapes, and geologists are very good at this. They're very good at looking at the shape of the crystals to get some information to help identify what that crystal is. Our process is called characterization. You know, we want to be able to characterize the crystals. So we don't want to lose that information if possible. But then again, we don't want to contaminate this. And so what we'd like to do today is we'd like to pour off any of the liquid that's in here if you have crystals. And then we want to wash these with ethanol. So normally what we'll do is filter, but hopefully you have big enough crystals that you can just decant. If your crystals are small still, then let them grow more. But what we want to do is we want to have big enough crystals so that we can just decant the solution. And then what we're going to do is we're going to wash the remaining crystals. But we're not going to wash it with water, because if we wash it with water, what's going to happen to our crystals? They'll dissolve. So we're going to wash it with 95% ethanol. A little bit will dissolve, so we might lose some of the edges and some of the corners a little bit, hope, but not too much, let's hope. And so we'll wash it with 95% ethanol. And hopefully that gets rid of any remaining contaminants in there, because it turns out these crystals are less soluble in ethanol than potassium oxalate and oxalic acid are. And so what we're going to do is we're just going to try to wash these off. Now ethanol dries pretty quick. And so what we're going to do here is we're going to air dry these. And so what the 95% ethanol is going to wash the solution away, and it's going to replace that solution with 95% ethanol. 95% ethanol is what we call a very volatile liquid. It evaporates quite quickly. I tried to, in organic chemistry lab, we made 95% ethanol by distillation. And so I wanted to taste what 95% ethanol tasted like, but you know, when I put some on the tongue, it evaporates so quickly that you could smell it and all, but it's not much of a taste to it. So that was air dry. We're going to air dry these. It should dry pretty quick, and then weigh them. This is going to be this is going to give us enough information to calculate the yield. And so we're interested in the percent yield. And so this is why we'll need to weigh these. Usually the higher the percent yield, the better. But what we're primarily interested in is getting good quality crystals, not necessarily in maximizing yield. And so we're trying to do two things. Get a decent yield, but also get good quality crystals. Now, why do we want crystals? Why we want big crystals is because in a crystal, if impurities get in there, can the crystals grow very big? In the case, impurities, it depends on what the impurities are. Sometimes impurities can mimic certain things. Like, for example, at Fukushima, they're worried about strontium, radioactive strontium, because radioactive strontium can mimic calcium and then get incorporated into your bones and teeth. Well, if you have radioactive strontium replacing calcium in your bones and teeth, that's not good, because now you're permanently radioactive, let's say. So sometimes impurities can get incorporated into structures, but it's difficult because it's not a perfect fit sometimes, and if it's not a perfect fit, then the crystals can't grow too big. And so what we want big crystals. In fact, when they do silicone wafers for chips, semiconductor chips, do you know those silicon wafers are gigantic single crystals? Just one big crystal. Even though they don't have the faces, they grow the crystals. They grow them to be round like this, and so they're missing the facets. We call these facets here. But it's just one gigantic single crystal, and then they can cut or slice the wafers off this. And the reason they want a big single crystal like this is because when you have a big crystal like that, it locks out impurities, because impurities screw up the lattice structure. And so now it's no longer perfectly aligned, it's off, and you aren't going to get big crystals. So normally we want big crystals because big crystals imply high purity. And so anyway, but what if you didn't get big crystals? What if you didn't get big crystals? Then what we're going to do is, okay, we're going to weigh this. We're going to get some kind of percent yield, and then we're going to divide this into just the original sample. And then some of these crystals, we're going to try a process called recrystallization. What they do with these, how do they get the silicon single crystal? They keep recrystallizing this. In fact, what they do is they melt it down here at the bottom, and then they bring it to the top. So they let it grow slowly. You know, the more slowly you let these crystals grow, the more time the atoms have to arrange themselves in their proper position. And eventually they just kind of melt and then solidify and melt and solidify, melt and solidify, and eventually the impurities kind of just rise to the top. And they can just get rid of the impurities that way, you know, because they get locked out, you know, when you have a nice big single crystal. And so sometimes we have to do this multiple times. So you can buy different grades of chemical. You know, the technical grade is the cheapest. The technical grade is just as is. So what you do is you just make your crystals, and whatever it is, that's what it is, and then you just wash it. Usually it's very fine crystals, not very big, and they do that. For higher grades of chemical, what they're going to do is they're going to do additional purification steps. And these additional purification steps is a lot more work, and it's also money, because you got to spend money for whatever chemicals you need and the time required. And so recrystallization is a very common technique that's used for purification. So if we stopped here, you know, our percentage, that is, the percentage purity might not be as high as we can get it. Usually technical grade, you're looking at 95%, 97% purity. If you want purity in the high nines, like 99.99% or 99.999, 5 nines, 6 nines of purity, you're going to be paying a lot of money for that. And one of the techniques, the common techniques, is recrystallization. So in recrystallization is we'll take some of the crystals here, so we'll take our crystals here, and then Xtals is usually what people use to abbreviate, and then just dissolve it in a minimum of DI water. And then we'll try to regrow the crystals. You know, so we'll add some ethanol, plus ethanol, but we don't want too many crystals to come out. Because in this process here, we have two things governing crystal growth. And there are books written about this. Because people want to be able to grow crystals, but sometimes it's very difficult. There's not like one method that works for everything. And so some people say it's the art and science of crystal growth. But let's talk about the science part of the crystal growth. The science part of the crystal growth involves two things that we worry about. One is nucleation, and the other is growth. Nucleation are these little baby crystals, and there's different ways we can nucleate crystals. What we want to do is, there are typically two extremes of nucleation. And so let me talk about these two extremes. One is that we just nucleate one crystal. So this is like one baby crystal here. And then let that grow into a big crystal. Here. The other extreme is we don't nucleate one crystal, we nucleate thousands and thousands of crystals. If we nucleate thousands and thousands of crystals, like this, then we end up with tiny crystals. Well, in terms of purity, I'd rather have one big crystal than thousands of tiny crystals. So the question comes up is, how can we nucleate fewer crystals? Maybe not one, but sometimes we can try to nucleate one. Some people try to nucleate one crystal by putting what's called a seed crystal in there. So that's potentially one method. Well, we have seed crystals. So we're going to try this. You have your original crystals here. You're going to take one of those crystals out and use it as a seed. A seed provides a template for new crystals to grow, because if the template's already there, like an anion wants a cation next to it so the cation can attach. And a cation wants an anion next to it, and that can attach. And so we're going to try using a seed crystal here. And hopefully that ends up in growing a big crystal. Other times when you nucleate, like for example, if you dump in the ethanol, you can nucleate thousands or hundreds of thousands of crystals. None of them are going to grow very big. And so, but then what happens if you throw your seed crystal in and it dissolves? You know, it's not saturated enough. You didn't dissolve in the minimum. We need to dissolve in the minimum so that when you put the seed crystal in there, it becomes super saturated and we expect precipitation. But sometimes you throw in the seed crystal in there and then it nucleates a whole bunch of baby crystals. And so nucleation and growth is tough. What we want to do is we want to nucleate the minimum amount of baby crystals and have those grow. So those can grow big and strong. I was watching this thing on TV with birds, and if there are too many baby birds, you know, then they run the risk of them not surviving because the resources are spread out too thin. So I saw like a baby bird being kicked out of the nest, which is sad, but anyway, here we want to try to avoid this. So we should have some time. You can take a look at your crystals and see or assess the situation. If you still don't have crystals, or if your crystals somehow dissolved, then what we need to do is we need to get them to nucleate and grow again. And so what you'll do is you'll get some ethanol and try to decrease the solubility to get them to grow again. Okay. Hopefully we can get some nice crystals to appear. Let me show. So I saved some crystals from past. So if you want to see what they look like, you can pass it around. You don't have to get crystals that big, or you know, if you get crystals bigger, that's even better. But those are pretty big crystals. Those are the biggest I've seen, so that's why I kept them. But most people don't get crystals that big, so don't worry about if your crystals don't look like that. Okay. All right. Are there any questions regarding this? Then I think next week with the video, because next week we're going to have Monday. And then I'm gonna miss Wednesday and then the following Monday. So I'm gonna put up some videos on the reports for this lab and the titration lab. The titration lab, we need to do some calculations for that. And so let me talk about that next here. And so the purpose of the titration lab is to ID an unknown acid. And we're going to ID the unknown acid. Some of it's going to be fairly straightforward. One, is it mono or diprotic? Two, what is its experimental molar mass? The molar mass, we need to know the volume, and if it's a monoprotic, we need to know the volume at the equivalence point. If it's diprotic, then we want the volume at the second equivalence point. The second equivalence point is more prominent, and it should lead to less error than if we go off the first equivalence point. But we could do both equivalence points. The second one's going to be more reliable because it's easier to analyze. And so from this, we can get the volume of sodium hydroxide. From the volume of sodium hydroxide, we could get the moles of sodium hydroxide. From the moles of sodium hydroxide, we could get the moles of acid. We don't know what the acid is, but if we know it's monoprotic or diprotic, then it's going to be this ratio. If it's monoprotic, it's going to be 1 mole of acid for every 1 mole of sodium hydroxide. This is for monoprotic. If it's diprotic, it's going to be 1 mole of acid to 2 moles of sodium hydroxide to get to the second equivalence point here. And so that's going to give us the moles of acid. Okay, once we have the moles of acid, then what we're going to do is we're going to just take the grams of acid that we got from the balance, so we'll take the mass of acid weighed and divide that by the moles of acid calculated. So we're just going to do this. That's going to give us the molar mass of the acid. And so now we have 2 pieces of information that we can use to identify our unknown. You know, the molar mass, experimental molar mass, and whether it's monoprotic or diprotic, in case there's some overlap with the molar masses. The other piece of information that we're going to use to identify our acid is the pKa values. The pKa value, what we're going to get is, if it's monoprotic, then the pKa is just the pH at the half equivalence point. If it's diprotic, then what we're going to get is we're going to get 2 pKa's. We're going to get pKa1, which is the pH at the half equivalence point, but it's the first half equivalence point. Or I should say the half first equivalence point. And so this is the pH at the 1/2 the first equivalence point. And then we're going to get pKa2, which is going to be the pH at 1/2 the second equivalence point. Which one would you suspect can be determined more accurately, more reliably? For diprotic acid, Would you have more confidence in pKa1, or would you have more confidence in pKa2, or would you have equal confidence in both pKa1 and pKa2? More in pKa2, that's correct. Why is that?
Isn't that a bigger curve?
Yeah, it's bigger, and then remember you had to bring the pH super low to see pKa1, which you might not have done. pKa1 could be way off, potentially. And so be aware of that. You can't treat these equally. For monoprotic, we don't have any choice. But monoprotic usually is okay because it's a little higher in pH. We don't run the risk of solution dilution, right? Being overly diluted. Now, what would be more reliable, molar mass or pKa in terms of identifying your unknown? What would you have more confidence in? Would you have equal confidence in pKa? Let's say, the reason I'm asking you this is because frequently there's a conflict. pKa says it's a better match with this acid, whereas molar mass says it's a better match with an entirely different acid. Which one would you have more confidence with if there's a conflict that arises? Hopefully there's no conflict. Hopefully the pKa is right on, the molar mass is right on. But sometimes that doesn't pan out. And so what would you have more confidence in, the molar mass or the pKa? Let's say your pH meter was reading off. Was your pH meter reading exactly the same as your neighbor's pH meter, would you say? When we did that lab where we measured a whole bunch of solutions, actually the pH lab with the solutions, you saw the variation in the data, right? So, so there are lots of things that can impact your pKa values. One, you know, what if you use your neighbor's pH meter? Would you have gotten the exact same pKa value? Two, what if you miscalibrated the pH meter? You know, if the pH meter was systematically off each time. And so there's lots of things that can impact pH measurements. So that the pH measurement lab that we did, I think what we'll do is you don't have to turn in a report for that. That was just some getting familiar with the pH meter. The numbers were kind of far from each other. The spread in numbers was kind of big, and so I decided not to do that. But anyway, getting back to this, I would have more confidence because if your pH meter were miscalibrated, the equivalence point is not going to change. You know, it's just going to go up or down, but it's not going to go left or right. The equivalence point will stay the same because the number of moles doesn't change. However, the pH can change. It could go up and down depending on how well calibrated or miscalibrated your pH meter is. And so I would have much more confidence in the molar mass. And so this is how we're going to weight these things. Since we weight these things in this way, there's a bit of interpretation involved, and this is why we're doing a formal report for this. We're doing a formal report for this because you can explain how you're analyzing your data. And this way, if you get the acid wrong, at least you know you have some argument for why you selected that acid. And maybe it's convincing based on the data. And so that would be a mitigating factor. You know, sometimes people get the wrong acid assignment. And so this is a good one for the versus, you know, for the qualitative analysis, it'd be too much to write a formal report for this. You know, so for the qualitative analysis, you either get it right or you get it wrong. You know, you're not going to be able to like argue, well, you know, why you thought it wasn't there or why you thought it was there. Okay. All right, I'm going to stop here. What you're going to do is you're going to check out the equipment, and then I'll just show you how to set up the LabQuest for data collection for this. And it should go pretty fast. So go ahead and check out the equipment. Today I don't think they're filming anything, so it should be easier.